Let us derive the expression for isentropic efficiency for our nozzle. We'll begin by evaluating the conservation of energy equation for a nozzle operating under steady state. We're going to neglect work, heat transfer, and the changes of potential energies. That is, since it's a steady problem, our time rate of change of energy is equal to 0. Q dot and W dot are both equal to 0, and GZ1 and GZ2 are both equal to 0. From the continuity equation, our mass flow rate into our system is equal to our mass flow rate out of our system, thus these divide out to unity. If we are given an inlet velocity v1, which is invariant, our isentropic velocity is a function of our isentropic enthalpy. That is, we can recast our conservation of energy equation to say h1 less h2s is proportional to the velocity at state 2 squared. And our velocity at state 2 is assumed our ideal velocity. In our actual case, our difference of enthalpies, h1 less h2, is going to be proportional to v2 squared, our actual velocity. If we substitute these expressions into our isentropic efficiency equation, we have the isentropic efficiency of our nozzle is h1 minus h2 per h1 minus h2s, which is equal to our actual velocity squared at our exit per the velocity of a situation where our entropy is constant at our exit squared. As an aside, the isentropic efficiency of nozzles is around 95%, and with proper design and contouring, it can be very close to unity.